Hi everyone, in this video we're going to cover the first section of Chapter 11. Chapter 11 deals with inferences on two samples, and in 11.1 we're drawing conclusions, making inferences about two population proportions. Okay, the first thing I want to look at here is the difference in the language in looking at these problems. In example 1, we have acne medication. We're applying medication A to part of a subject's face, medication B to another part of their face, and we're talking about taking the proportion of subjects whose acne is cleared up is then determined. So clearly the wording, right, proportion there, and we have two different medications both being applied to the same person's face. Okay, so that's how we're comparing two different samples, right? In example 2, we have 30 credit card and 30 cash receipts at a restaurant, and the goal is to determine whether the credit card purchases have a higher average than the cash purchases. So instead of, in the previous chapter, comparing sample data against a known value or a hypothesized value, in this section we're comparing two different samples to each other. One important piece to be aware of as we go through this chapter is whether the samples are independent or dependent samples, right? Independent, when the individuals selected in one sample do not dictate which ones are in the second sample, and then dependent, when when the individuals selected in one are used to determine the individuals in the second. Okay, and think back to the previous example. You could certainly tell that the first one, the sampling method was dependent, right? The two sides of their face. Second one, they were independent. There was nothing telling us that the credit card and the cash receipts were matched in any way at all. Pause the video if you want to read through A and B to determine whether they're dependent or independent. But if you did pause and write them down, you will be happy to know that the first sampling method was independent, and the second sampling method was dependent. Right, my dominant hand and non-dominant hand are both matched to me. Right, that one is that's dependent sampling, and the other one independent. There was nothing stating that they were matched in any way at all, so independent sampling. In the earlier sections, we always have those slides with lots of formulas. This section is no different, but we'll look at these and then we'll kind of tweak them in a minute. But I'll highlight the important stuff off of this slide. Okay, so we have two samples, right? Sample 1 has a size N1, and X1 of the individuals have some characteristic. So we get one proportion. P1 hat equals X1 over N1. That's just taking the sample proportion from one of your samples. Same deal with P2 hat. That's from the other sample. So we collect two samples. We have two sample proportions, and we'll make a note with our subscripts here. Okay. Then the mean, we write it this way: the mean of P1 hat minus P2 hat, P1 minus P2. Okay, that won't come up super often, but just be familiar with this notation, right? But we have a mean and a standard deviation of this distribution, and also this big giant monstrosity of a z-score formula, but I'm going to condense it in just a minute. The main thing that I want you to take away from this slide is how we have our P1 hat and our P2 hat, and just know that, I mean, the mean and the standard deviation of this distribution, we can compute that. This is how it works kind of in general, but the problems that we will encounter specifically, I will have more condensed formulas in just a second. Okay, so these are the formulas for what is called the pooled estimate of P. So we're going to take and find three different proportions. We'll have our P1 hat and P2 hat from the previous slide. Right? Those are each individual sample proportion separately. And then the pooled estimate of P is taking the two samples and adding them together. X1 plus X2, N1 plus N2. That is called the pooled estimate. Okay? And that pooled estimate appears in the test statistic formula right there and there. In the numerator, it's the difference between the sample proportions. In the denominator, we use the pooled estimate and then each sample size independently over there. Okay, so you'll have these formulas in front of you. The focus will be putting the right number in the right location, and then can you push the buttons correctly. And here we have the slide that we've seen a couple of times now in Chapter 10, outlining the steps to perform a hypothesis test. They are virtually the same. I'm just going to highlight the differences here. In Step 1, we have a slight difference. Notice here with the null and alternative hypothesis, instead of, in the previous section, our null being p equals some number and then p does not equal some number, right? That was Chapter 10, where we were comparing against a number. Now we're comparing two samples. So it's sample 1 equals population proportion 1 equals population proportion 2, or it doesn't equal. So that's one key difference there in how we write that down. And it's really just going to be the p's that we write down. There's not going to be any numbers up there. We're saying, are the two samples equal to each other or not? So that's the main difference here. As we scroll down through the steps, Step 2, level of significance, that's the same. Step 3, test statistic, well, that's the same, but we just have our new formula here with our pooled estimate formula. So that's newish, but it's still the same process. Our critical region, critical value, we're still going to do that up with Step 2. And then comparing the critical value to the test statistic, that's the same. State the conclusion, that's the same. Okay, so new formulas, a slightly different way of writing the null and alternative hypothesis. Otherwise, it's all the same. Same concept, same process. Now we get to our first example, and pause the video if you want to read through it once and try to pick out the important pieces. Okay, so now I'm going to highlight them. We have Nasonex. This many people tried Nasonex. And the groups were divided so that this many people were in group 1, and this many people got headaches. This many people were in group 2, and that many people got headaches. Is there significant evidence to conclude that the proportion of Nasonex users that experience headaches as a side effect is greater than the proportion in the control group? That's the question that we're asking, and it's at the 5% level of significance. I'll circle it instead because I put away my highlighter. All right, let's go through our steps. 1, the null and alternative hypothesis. This is how difficult it is to write the null down. P1 equals P2. Always in this section. Are the two proportions equal, or is one greater than the other or lesser than the other? And we got to find that key word there. Nasonex as a side effect is greater than the control group. Okay, group 1 is Nasonex, so we should probably label that too. So we're going to call P1 our Nasonex people, and P2, that is our control group, our placebo people. Okay, and so since they say the Nasonex is a proportion greater, we're going to say P1 is greater than P2, which tells me that I'm testing the right tail. So in Step 2, my level of significance, right? I'm going to draw my distribution. It is a normal distribution. There we go. I'm going to label the right tail. Let's switch to red here. Label the right tail and shade to the right. There's a z-score corresponding to that level of significance. Alpha equals 0.05. All right. You will find that at the bottom of the Z table, table 5, and it is 1.645. 1.645 is that Z-score right there. Anything to the right of that, we reject. Anything that's to the left of that, we do not reject. All right, step 3, the test statistic. Okay, so this one we got to do a little bit more work for maybe than in the past, because in my formula I have some P hats. There's a P1 hat, there's a P2 hat, and there's a P hat in that formula. And so I need to write down each of those proportions. Okay, P1 hat, that was the 547 out of 2103 over 2103. P2 hat, that was 368 over 1671. 1,671. And then p hat, that is the pooled estimate. Put the two samples together. And that is, let's see, I'm going to add 547 plus 368, and you get 915. Oops, there's a 1 in there. 547, 36, yep. 2103 plus 1671 equals 3774. Okay, so there's my three proportions. Now I've got to type each of them into my calculator and get the decimal approximations. First one is 0.260, 368, 71. That one is 0.220, 915 over 3774. And that last one is 0.242. Okay, so 22% for the control group, 26% for Nasonex. More people got headaches, but the question is it statistically significant? Now, I'm going to write down the z-score formula again because, well, we only saw it for a minute on the last slide. P1 hat, P2 hat over the square root P hat, 1 minus P hat, another square root, 1 over N1, 1 over N2. There's a lot going on there, and you've got to make sure, number one, that you put all the numbers in the right places, and number two, that you push all the buttons correctly. All right, so up in the numerator, first P1 hat, 260, then P2 hat, 220. Under the first square root, that's the pooled estimate, twice 1 minus 242. And then the other square root, 1 over the first sample size, 1 over the second sample size. Okay, that's where everything goes. Now, last piece to this step 3 is I have to type all of that mess into my calculator. And what I would suggest is maybe do it in a couple steps. Maybe I'll type in the numerator first. 260 minus 22 is 0.04. Okay, that's out of the way. Now I'm going to type in the denominator. I'm going to go the square root of 242 times 1 minus 242. I'm going to hit enter on that, and then I'll type my second square root, 1 over, times my second square root, 1 over 2103 plus 1 over 1671, close that parentheses. I got 0.0140, etc. My suggestion would be to pause the video here and see if you can get that same answer for the denominator. So I typed in the first square root, and then I hit enter, and then I hit times the second square root. You could do it differently. That was just kind of the way that I went with. If you want to do it all in one step, you have to remember to close that parentheses. Okay? Then when I type in 0.04 divided by, and I'm hitting my second ants, I'm using that whole big long chain of numbers that was in my calculator, stored in my calculator. I get 2.85 for my z-score test statistic. Okay? If you have trouble getting that, let me know. I can post a little help guide on typing this into your calculator on a different day, that if that would be beneficial. Okay, so now what do? We take this 2.85 z-score. Where does it fall? Where does it fall? It's over here. It's in the red zone. It's in the critical region. It's past the critical value. What does that mean? Reject. Reject. Step 4, reject the null. Reject the null hypothesis. There is evidence that Nasonex gives you headaches at a greater rate than normal. Okay, I typed this out. Let's find it. There it is. Here's my fancy formal sentence. Again, you don't have to word it verbatim like that, but that is one way to word the conclusion to this problem. And I am going to want to see that concluding sentence on your test. And you can copy this format. You can choose to phrase it in your own way, but that's the ultimate answer to the question. We're going to look at one more example where we have an online business and we're trying to pick between two different designs for our web page. We hired a firm to design to send us two different designs, and we want to see which one's better. So design 1, you can see there we're given a proportion. Design 2, there's our proportion. Based on these results, which one should you go with? And so this one is worded a little bit less specifically. Okay, and I'll talk about that as we go through the regular steps. Step 1, the null and alternative hypothesis. Null is always in this section. P1 equals P2. And if you read the problem a couple of times, you're not going to find that buzzword, greater than, less than. You're not even going to find differently. I mean, they're different web pages. Which web page should you go with? So we're just going to take this as a two-tailed test. P1, whoops, why didn't I write a 1 there? P1 does not equal P2. We'll keep this two-tailed, okay? Because there's nothing cluing us in one way or another. In step 2, the level of significance, we're not given that. Well, I'm not going to put a question mark there. I'll write alpha equals, I don't know, we weren't given it, but I'm still going to draw my distribution, okay? And I'm going to label both tails with a little red zone, critical region, but I don't know what my cutoff is. And that's okay. This problem was given, like I said, a little bit less specifically, just kind of thrown out there. But we'll come back to that in a minute once we have step 3 done. Test statistic. Okay, so for this, we need our different proportions. Oh, and one thing I didn't do, it's maybe obvious. P1 is going to be design 1, and P2 is design 2. We should label that here. All right, so let's say P1 hat. That is 54 over 523. P2 hat is 62 over 512. And P hat is, let's see, if I add 54 plus 62, I get 116. If I add 512 plus 523, I get 1,035. And then let's get each of these in decimal form. 0.103. 62 over 512, 0.121. 116 over 1035, 0.112. Decimal point 112. Okay, so there is the information needed for our test statistic formula. And when we plug in, the numerator is P1 minus P2. So this is Z naught is equal to 0.103 minus 0.121 over the square root. Now I use my pooled estimate. And then the other square root, 1 over the sample sizes. There we go. Okay, typing this into my calculator. A couple of steps here. 0.103 minus 0.121. Negative 0.18. And then in my denominator, I'm typing that in, and I get 0.0196, etc. And I'm going to keep that number stored in my calculator, 0.018 divided by second ants, and I get, oh, it's negative. Yep, negative 0.018, negative 0.918, or negative 0.92. Okay, so that's not that extreme of a z-score. Right? Where would that fall? How do I don't have my critical regions clearly defined, but for levels of significance of 10%, 5%, and 1%, all of them are more than 1 standard deviation away. Right? So this is a relatively, a z-score that is relatively close to 0. And so is there evidence to indicate that one of these designs is better than the other? The answer is not really. Right? They were pretty similar. One is 12%, one is 10%. So there is a difference there, but that difference is not really statistically significant. So they could pick either one. or they could just pick the one that they think is prettier, right? That's the type of conclusion that we draw here. So in this case, I wouldn't reject the null hypothesis, even though we don't have something, and I wouldn't do this to you on a test. That would just be mean of me. Even though we don't have, that looks like a face now. Even though we don't have cutoffs here, I would still say for step 4, don't reject. Don't reject the null hypothesis, right? On a test, I will always give you an alpha level of significance, but just for the heck of it here, I just kind of wanted to be a little bit more general. Okay. Just one final note here at the end of the section. The book does cover dependent samples and hypothesis tests. We do not in this class, so don't worry about them. So if you are a reader of the book, if you do look through the book, don't try any of those problems. Don't worry about that content. Hopefully it's not on the homework, and it definitely won't be on the test. If you do see anything weird about dependent samples, please shoot me an email. Have a wonderful day, and thank you for listening.